Well, basically, we have looked into different types of corrosion before we end our lecture last week. We have looked into general corrosion. This is one of the most, I think, easiest or the most available types of corrosion that you can see surrounds you. And then after that, we have localized corrosion. So for localized corrosion, we have pitting corrosion, crevice corrosion, galvanic corrosion, intergranular, selective, and filiform corrosion. Okay, so pitting corrosion actually occurs when you have a failing of a passivative layer. Therefore, the fail is actually with regards to any scratch, any I think damage on the passive layer, which enables oxygen and water to penetrate to this protective layer and resulting corrosion downwards, propagation, and forming a small pits. Meanwhile, for crevice corrosion, it's actually as a consequence when you have a concentration different. So this can be resulted when you have a gap, cavity, a recession, and whatsoever in your structure, which actually can trap any sort of dirt or small particles. So when you have a dirt or small particles, so this actually can absorb water or whatsoever, and making that area will be highly concentrated with oxygen or water and easy to corrode. Galvanic corrosion, meantime, is actually by attaching two different metals with two different reactivity in the same electrolyte, in the same environment. And with that connection, it actually, I think, giving a galvanic effect. So the one that is more active will become anode, and the one that is more noble will become cathode. Intergranular corrosion, meantime, is actually a corrosion that occurs along the grain boundaries. This often occurs when you have alloys, for example. When you have alloys that didn't mix together, it is not homogenized, then you will have a different phase, and these phases has been separated by a phase boundary. So the corrosion process can easily occur in the phase boundary and resulting in cracks and whatsoever. Selective corrosion, it is where you have a leaching, selective leaching process, where most of the active element will be leached out and impair with the main structure. So this also for alloys, when you have a mixture between like zinc with other types like copper or metals, iron, zinc, or whatsoever. And you know that zinc is more reactive, so zinc can easily oxidize or leach out from the structure. And finally, we have this filiform corrosion. Filiform corrosion occurs when you have, I think, a coating, a surface coating on the surface, but it is brittle or it is porous, which enables oxygen and water to corrode underneath the coating layer. So it forms like a warm track or whatsoever. So this also can be seen in your hostel or in your department whatsoever. Today we are going to continue with the combined effect of mechanical factors and corrosion. So in this case, we have two factors. The first one is actually corrosion, a naturally occurring process. And the second one is actually by means of mechanical factors. So for combined effect of mechanical factors and corrosion, we can categorize it into different parts. You have a stress corrosion, corrosion fatigue, erosion corrosion, and fretting corrosion. The first one, basically on stress corrosion, can be resulted from the combination of applied tensile stress and a corrosive environment. In fact, some materials only become susceptible to corrosion in a given environment once a tensile stress is applied. Stress corrosion occurs when the metal is corrosive in environment, is exposed to a static stress that results in fracture. So please remember that for stress corrosion, it is always related with static stress that results with the fracture. So in this case, what it means is that you have a load. Okay, the load is actually giving the stress, but at the same time, it is a fixed load. It has, or it gives a static amount of stress. So with this, I think that is why we don't have I think how do you say, transgranular or trans um, cracking as compared to the other one, corrosion fatigue. So as I said, for stress corrosion, we have to understand that it is static stress. It is a fixed amount of stress. Fixed amount of stress. Okay, right. Corrosion fatigue actually caused by combined effect of corrosive environment and varying states of stress. It is almost similar with stress corrosion, but you have a different amount of stress, different load or amount of stress. Okay, so it will actually result transgranular. Corrosion, the fatigue fracture is brittle and the crack are most often transgranular, as in stress corrosion cracking, but not branch. Okay, it's normally a bigger, crack like this. It's not like hyper branch. Hyper branch, you have a small crack and whatsoever. I think small cracks, you can see it from stress corrosion, okay, where you have a transgranular and I think a hyper branch. You have a hyper branch cracking. Fretting corrosion, meanwhile, is actually a corrosion that caused by rubbing the two contacting surface under load. Yeah, you have a fretting, you have a friction. Yeah, so this is actually in the case of if you have a structure like lever, pembuka pintu, you have I think a joint, a loose joint whatsoever. Yeah, so when you have I think a movement of one structure to another, so this can cause friction or so-called fretting, rubbing of the two contact surface under load, which lead to a steady erosion of material. And then we have erosion corrosion. Okay, so erosion corrosion arises from a combination of chemical attack and the physical abrasion as a consequence of the fluid motion. Erosion itself, erosion in Malay bermaksud hakisan. Hakisan. Menghakis lah. Corrosion is kakisan. Kakis. Yeah, so it's actually a different thing. You have a kakisan or corrosion, which results from the electrochemical process. Erosion is more of physical contact. You have a flow of, I think, a fluid or whatsoever that has an abrasion effect. Erosion corrosion arises from a combination of the chemical attack and the physical abrasion as a consequence of the fluid motion. Okay, so you know that if you have like this angle and the movement of fluid, and at the end of the day, you have like more abrasion at this region, and that is why you see like there's a lot of bubbles or whatsoever, and finally it can be corroded in the end. Cavitation corrosion is an erosion caused by combined effect of corrosion and the pressure caused by the breaking of the gas bubble formed in the liquid of cavitation. Sometimes you'll see that there's an interconnection between this process, okay? And you know that bubbles actually produce when you have a flow or high pressure, okay? So if you actually put, I think the fluid at high velocity or any fluid at the high velocity, so what happens is that the bubbles, oxygen or whatsoever, will travel together and it will stick on the surface. So that is why you will see that over here you have cavitation, cavity lah. Okay, so it is actually as a result of if you have a structure, then after that you have too many bubbles, okay, on the surface. So inside this bubble you have gas, of course, oxygen gas, and it is trapped. So it can actually promote a corrosion process, and finally you'll see like the surface is become corroded like this. Okay. Next one we have microbiological corrosion. Okay, or so-called MIC. Microbiological induced corrosion. Ini bukan nama parti, bukan MIC, parti tu. This is actually microbiological induced corrosion. So in this case, the corrosion process is actually triggered by the presence of microorganisms such as bacteria. So don't think that bacteria cannot eat metals. It can. So for MIC, you will have IRB or SRB. So what does it mean by IRB? IRB, it means iron reducing bacteria. SRB is actually sulfur reducing bacteria. Okay, so it has a different species. Adalah dia punya species salmonella or whatsoever. It can be categorized either as iron reducing or sulfur reducing. So sulfur reducing normally happens in oil and gas environment, because it has a lot of H2S and sulfur, and this bacteria can survive with the presence of sulfur. So it can actually convert the presence of sulfur into H2S and make it more corrosive. IRB, okay, the bacteria attach on the surface of the metals, and you know that for the bacteria, it has this small tentacles, and then it has a slime as well. So this slime, when it attach on the surface of the metals, okay, it can actually digest, digest anything, because that is actually the function of the bacteria. Dia tak ada mulut. So what it do is it will excrete chemicals, and what happen is that the host will be digested and then it will be consumed. So this bacteria actually consume lah. Kita consider it consumed the metals, and finally when it consumed, of course, it will be corroded. Okay, so microbiological corrosion is caused by the accumulation of microorganisms which are found in contaminated fluids, and is normally confined to the internal surface of integral fuel tanks. Okay, so we are moving on to the last part, which is on the corrosion protection. Okay, I believe I have assigned you with this, group presentation, video presentation on corrosion protection. So I'm not going to go too detailed. I just go superficial. We are going to finish this by today, because you, at the same time, you are also doing the presentation, but it's just some information. So you guys can also ask if you don't really understand about the types of corrosion protection that currently you are reading and currently you are presenting. Okay, so I've told you that there's 5 major techniques for corrosion control. Okay, first one is for the material selection. Second one is by modifying the environment. Okay, so modifying the environment by making it less corrosive. So that is why you will see that you will add inhibitor, corrosion inhibitor or whatsoever. Okay, so install a protective coating. So this is more or less for paint, or either inorganic or organic coatings. Imposing electric current to supply electrons. So this one is more or less, by putting currents into the metals, and actually inducing or actually reducing the corrosion process. So that is why you'll see that there is cathodic protection, okay, and then you have anodic protection. Even for cathodic protection, you will have a normal CP or ICCP, induced current cathodic protection. So this one actually it use rectifier lah. Okay, normal cathodic protection it doesn't have rectifier. This is actually for small area, and ICCP is more or less for a bigger area. Bigger area, then you need to apply the rectifier. So what does it mean by cathodic protection? Cathodic protection is metal to be protected will become cathode. Okay, and anodic protection is actually in contrast. This only happen in the environment of acidic or alkaline environment. And finally, we have a proper design to reduce, okay, erosion and combined effect of corrosion. Okay, so we go one by one. The first one is actually material selection. In order to produce a metal, so we have to understand that we need a specific types of element that can prevent corrosion or resistive to corrosion. Okay, in marine environment, we know that if we use iron, it will be poor because definitely it will corrode. And the marine environment is with the presence of chloride ions and different types of mineral can trigger corrosion. Okay. Meanwhile, if you use copper, because copper is more noble, the standard potential is more positive, then it will be a good substitute. Therefore, if you have a combination between the one that is, I think, noble and the one that is maybe active, just to maintain the structure, then you have a better. Okay, another one is actually titanium. So titanium, you will see that some of the current technology use titanium. Racket badminton pun pakai titanium, bicycle pun pakai titanium because actually it is light, very light, ringan. At the same time, it is corrosion resistive. For high pressure, okay, normally people will use stainless steel. If you use steel alone, it is not good because it will definitely will corrode. So if you use stainless steel by doping different amounts of chromium, nickel, molybdenum, it will be better. So that is why for stainless steel you have many grades. 316, 318. 318 is the best. And then you have 304, 306. That is actually a low grade. Okay. And for the damp environment, okay, if you use a pure metal, it is unsuitable. But if you make an alloy, then it is much better because it can actually reduce the surface degradation and finally reduce the corrosion process. Right. So still at the same, I think, part, modifying the properties of the metals. All the while we are talking about examples of alloying. So we know that by making the metal become alloys, alloys we know that you incorporate more than two types of element into the metal, then it will be or it will give a more corrosion resistant properties. For example, stainless steel, in which ordinary steel is alloyed with chromium and nickel. Stainless steel is protected by an invisibly thin, naturally formed film of chromium oxide. So this is actually how stainless steel is not going to corrode. You see that stainless steel is made from steel, but it cannot corrode because it has this chromium oxide film or layer. From the galvanic series, we can see that the more noble metals are less likely to corrode. When these metals are metallurgically combined with those from lower in the in the series, the resulting alloys takes on corrosion resistant properties. The resistance can come from the development of protective oxide film on the outside surface, or because the new alloy has a different voltage potential which act to make it behave more noble. Okay, so passivity is actually an alloying effect. Passive oxide film can inhibit aqueous corrosion as well. Okay, and we have seen a lot of examples on stainless steel, and we know that alloying iron with more than 12% of chromium will result in formation of protective chromium-rich passive film, which result a large increase in corrosion resistance. And if you can see from there, different grades of stainless steel have different amount of elements of chromium dope. So for example, stainless steel 304, you have 18% of chromium plus 8% of nickel. Meanwhile, for stainless steel SS316, further addition of 18 to 8 stainless steel of about 2% of molybdenum, which actually increases corrosion resistance more, even more. Right. So before we move on to the modifying the environment, is there any question regarding on modifying the properties of the metal? Okay. So we move on to modifying the environment. Actually, all the while we talk about corrosion, it is always related with the environment. And the environment that we are talking about is, of course, with regards to the humidity, relative humidity, presence of oxygen, and presence of other impurities like concentrations of H plus, pressure, ionic contaminants like, for example, chloride ions, okay, or etc. So this is actually one of the most challenging things if you want to reduce the environment. Okay, so modifying the environment can be done by first controlling the environment. Okay, controlling the environment can be done by controlling the relative humidity. If you actually know that the environment is very damp, very humid, with the RH relative humidity more than 50%, okay, then you know that your environment is highly corrosive. But you can actually reduce the relative humidity by using humidifier. Okay, so humidifier can make the environment more humid or less humid. So in this case, you can set actually the humidifier. In this case, the surface must be a confined space, ruang yang bertutup. Then only the relative humidity can be controlled. So it will actually absorb most of the water or humid in the environment and reducing the relative humidity value. So when you have lower relative humidity value, then the environment is no longer corrosive. Second one, by removal of oxygen. So removal of oxygen can be done by putting oxygen scavenger. Okay, oxygen scavengers is almost the same like corrosion inhibitor. What happens is that by removing the oxygen from water system in pH range 6 to 8, one of the components required for corrosion will be absent. Okay. The removal of oxygen can be achieved by using a strong reducing agent, such as sulfide or hydrazine. Okay. Hydrazine, macam mana dia punya structure? Hydrazine is like this. Okay. So if you add with oxygen, so what happens is that it will form nitrogen gas plus with H2O. So you will actually reduce the corrosion content and it will become nitrogen. Nitrogen is a noble, inert gas, and water. Okay. And then next, you can actually control the environment by controlling the pH. Of course, if you know the pH, if it is in a tank or what, you can actually make it neutralize if it is too acidic. Pressure, if the pressure is too high, because you know a pressure too high can actually break or damage the metal, so you can actually control the pressure. Ionic contaminants, if your supply city water or whatsoever, it contains more than 5%. This is actually the permitted amount. It must be less than 5 ppm. Chloride ion content dekat air pipe ke apa semua, it must be less than 5 ppm. Okay, so how to control ionic contaminants? So that is why you need to use what? Filter, okay, or membrane. Because in this case, the ionic contaminants can easily be discarded, and you wouldn't have more or other types of impurities in your saline or solution. And the last one, quite popular one that people use in oil and gas, in different types of I think industries, automotive and others, is by using corrosion inhibitor. Okay, so what does it mean by corrosion inhibitor? Corrosion inhibitor, it means that a chemical that is used normally in a small amount, small concentration or small amount, okay, normally ranging from 0.01 weight until maybe 100,000 or 100. This one is in percent weight, 100,000 weight. But normally the lower it is, the better. So if you have a corrosion inhibitor that even if you put in a small amount, it is effective, then this is actually the best corrosion inhibitor. Okay, a small amount of chemical that is when added to the environment, it can actually reduce the corrosion rate of a metal. Macam tadilah kita tengok hydrazine. If you put hydrazine inside the solution, so what happen is it will actually reduce the oxygen and become other things. But corrosion inhibitor is not necessarily have to be oxygen scavenger. It can actually function as other things. Right. You can have different types of corrosion inhibitor. You can have either inorganic inhibitor or organic inhibitor. Examples for inorganic inhibitor, you will have chromates, phosphate, nitrates, and etc. Meanwhile, for organic inhibitor, okay, so the criteria must be aromatic. Aromatic means that it is electron-rich structure. Okay. Other than that, it contains heteroatom. Okay, heteroatoms: phosphorus, nitrogen, oxygen, sulfur. Okay. With all this criteria, it can be a very good organic corrosion inhibitor. For example, the simplest structure I can be guess or can suggest to you is phenol. Okay, for example, phenol. Phenol, you see that it has aromatic ring and it has heteroatoms of I think OH, hydroxyl. It has a lone pair. So this, and from this structure, it is electron rich. Okay, so it can actually easily interact with the metal surface. For example, if you have a metal surface of iron, when iron oxidizes, it becomes iron 2+, isn't it? Okay, so if you have phenol, for example, added into the environment, okay, so and the phenol can easily interact because you have OH minus, okay, and 2 electrons have been removed from the d orbital of iron. So d orbital of iron have less 2 electron, so it can actually share. It forms an interaction, okay, form a bonding, compensation or whatsoever, okay, and this interaction is known to be chemical adsorption, because it forms a bonding. Sharing of electron forms a bonding. Okay, or another types, you can have Fe2 plus. It tends to attract, I think, different type of species. Cl minus, for example, because you have a opposite charge. And then at the same time, your inhibitor can be protonated in the presence of acid. For example, if let's say that I put this phenol inhibitor in acidic solution and at the same time you put iron. Okay, so what happens is that phenol will be protonated. Okay, plus it will actually form electrostatic interaction between the protonated phenols with the negatively charged covered surface of iron. So dia ni covered by the chloride ions that is firstly absorbed on the surface. So with this type of interaction, electrostatic, it is physical absorption. Okay, physical absorption. Some of the mechanism and of its effect are formation of passivation layer, okay, formation of thin film on the surface of the metal that stop access of the corrosive substance into the metal, inhibiting either oxidation or reduction part of the redox system. So we already know that in corrosion process, it is redox. Oxidation occurs at anode and reduction occurs at the cathode. Okay, so by introducing corrosion inhibitor, it can actually jeopardize either oxidation process or reduction process. In this case, if let's say that you form the interaction between the inhibitor species with the iron, so what happens is that Fe2 plus, it cannot further oxidize or it cannot further combine with hydroxyl ion to form rust. Dia dah jadi stable kat sini. It forms a temporary product over here that actually make it stable and unable for OH minus to react. Tak boleh. Okay, so because of there's no interaction between Fe2 plus with OH minus, then rust cannot form. So that is actually the idea. And then for corrosion inhibitors, even though I told you that is inorganic or organic inhibitor, but that one is the class of inhibitor. So we can actually categorize also inhibitors as anodic inhibitor. So anodic inhibitor, it means that inhibitor that jeopardize or disturb oxidation process. So we call it as anodic inhibitor. Okay. Meanwhile, for cathodic inhibitor, it is a type of inhibitor that disturb reduction process. Okay. And you can also have mixed inhibitor where it disturb both oxidation and reduction process. The role of corrosion inhibitor, it reacts with a corrosive agent. Okay. At the same time, it can form a passive layer because when I told you that the interaction between the corrosion inhibitor with the metal surface, it can form a compensation, a bonding, a temporary bonding, electrostatic bonding or whatsoever, then it will form a layer, a protective layer. Forms an absorptive film or protective layer on the metal surface. So in this case, I think in this example, you have a phosphate ether. Phosphate is very rich. If you see from here, phosphate ni, PO4, it has too many unpaired electron, or how to say, localized electron. Okay, so it can easily donate the electrons and form a bonding with the metal surface. It can easily complex. So this will form a temporary film, invisible film. Right. The next one, the next technique is actually protective coating. Okay, protective coating is one of the common technique that people use in industry. The function of protective coating is actually to isolate the metal from the corrosion environment. So when you apply coating, what happens is that it will create a barrier. Dia mengasingkan the environment of metals and also the surroundings. Okay. Coating or covering with a more noble metals or better corrosion resistant properties. Non-metallic coating, for example, inorganic and organic coating. So you have the first one, metallic coating. So metallic coating is one of examples of electroplating, or electro deposition. Okay. In this case, the metal will be coated with another types of metals using electrolysis process. You learn this in the high school. When you want to protect the materials, you dip in copper, for example, copper solution inside copper sulfate solution. So copper will deposit on the surface and making the surface become noble. Okay. So this actually we call it as metallic coating. So coating with a more noble metals, the technique is actually electroplating or electro deposition. For example, iron coated with chromium, nickel, and tin for decoration purpose. Coating with zinc in galvanized steel, coating with tin or iron on iron for containers. Non-metallic coatings, okay, non-metallic coatings, we can categorize it into two parts: inorganic coatings and also organic coatings. As mentioned, the function of coating is to create a barrier. Okay, it can act as a physical barrier and bar access to the metal surface, or they can introduce a very high resistance into the corrosion cell circuit and drastically reduce the electron flow. The barrier type coating protects the metal as long as there are no cracks. If a crack occurs, corrosion becomes intense at the surface. Resistant type coating include additives that break down in the presence of water and oxygen into inhibiting agent. Okay. So for inorganic coatings, mostly it doesn't use organic materials. For example, concrete. Okay. Sand or silica or ceramics, clay. You've seen this in construction mainly. In construction, you will see that there's a reinforced steel. Ada batang cerucuk tu. Okay. So this reinforced steel is normally not coated. So what they do, because you still need reinforced steel to make the structure become better as a skeleton of the building. Okay. So in order to preserve the reinforced steel from corrosion, then you put concrete lah. Kita bubuh semen concrete to cover, to make a pillars. Inside the pillars, you will see there's a reinforced steel. Okay. Alright. So for organic coatings, you apply organic material, like for example, paint, plastic, tar, resin, or whatsoever. Resin, paint, plastic. Okay. Paint coating are considered the most practical and economical means for the corrosion protection. Okay. So there are several mechanisms by which paint coating system provide corrosion protection. The first one is actually by creating a barrier. It limits the access of chemical species involved in the electrochemical corrosion reaction. So it limits the presence of oxygen and water. Okay. At the same time, it maintaining a high electrical resistance at the substrate interference. Okay. Restricting the access of the ionic species. Almost the same. Okay. At the same time, okay, in coatings, it is also including additive. And part of the additive is a corrosion inhibitor. Corrosion inhibitor in primer will passivate the underlying metal surface. For example, dalam chart, okay, you will see that there is a zinc chromate, ada chromate, Chromate, you know, is a corrosion inhibitor, inorganic corrosion inhibitor. It will actually passivate the metal surface, making it become I think passive and reducing the risk for corrosion. And finally, cathodic protection. In some paint, like I mentioned earlier, you have apa tu? Zinc chromate epoxy coating. Ini yang selalu orang guna nak cat pada besi, tiang, pagar dan sebagainya. Because you will see that the types of polymer they use is epoxy. Okay, the corrosion inhibitor that they use is chromate, and then the cathodic protection effect is they include zinc. Okay? Because when you apply, you know that the one that is more reactive is zinc, and it can easily oxidize rather than the metals that you protect. So the coating actually provides 3-in-1 protection. It creates a barrier, at the same time it give a inhibition, and at the same time also it give cathodic protection. Right. So those who wanted to produce paint, so you know that this is actually the main ingredient to produce paint. First thing that you need is, of course, plasticizer or binder. You need a plasticizer or binder. In this case, you can use resin, you can use polyvinyl, you can use polyurethane, epoxy, alkyd, and whatsoever as your binder. Second, you need solvent, of course. For organic material like polymer, okay, it can easily dissolve in organic solvent. Okay, like what? Xylene, toluene, MEK, methyl ethyl ketone, MIBK, methyl isobutyl ketone, and many things. Okay, all these are actually solution that dissolve the binder. You can also have water-based coating, okay, normally for emulsion paint. Siapa tahu emulsion paint ni kita guna kat mana? So emulsion paint is normally used, this actually yang cat putih tu lah, that you use to paint your wall. So emulsion paint actually use water only. Okay, water and maybe titanium oxide as the main ingredient. Okay, and then you will have pigments or coloring. You have a pigmentation agent like, as I said, titanium oxide. Coloring, maybe you have a different color, Congo red, color whatsoever, and then you have additive. Additive that give anti-corrosive properties, like for example chromates, antifungal, maybe they put antioxidant, anti-mosquito or whatsoever. So don't be surprised that paint these days also have this anti-mosquito properties. So how they actually do the anti-mosquito paint? They actually know that mosquito didn't, they didn't like a smell or odor that I think maybe produce CO2, for example. Okay, so what happened is that if you put lemongrass or Simonella, lemongrass punya essence, so what happened is that mosquito dia tak mati, the mosquito is not die, but is actually they will run away because of the smell. The environment is not suitable for them. Okay, and the perfect way to coat your metal is by actually putting a primer first to actually increase the adhesion, and then after that followed by anti-corrosive paint, intermediate, and finally top coats for decoration, glossy and other things. Next one, okay, impose electric current. Okay, in this case, you might heard about cathodic protection. As I mentioned earlier, cathodic protection is a technique to control corrosion of a metal surface by making the surface become cathode. So you want to make the surface become cathode, noble, okay, to the environment of the cathode of the corrosion cell. So in this case, in order to achieve cathodic protection, you must pair your metals, for example Fe, with another species that is more active. For example, aluminium, magnesium, zinc, or whatsoever. So with this, you know that this will be cathode and this will be anode, or we refer it as sacrificial anode because it sacrifices itself, right? And in order to achieve cathodic protection, there's a certain rules. It must be connected. You must connect your metals with anode, the sacrificial anode, and by passing electric current DC, so that the metal surface become cathodic and did not corrode. So this is actually the principle, and it is also must be in the same environment, same electrolyte lah, or environment. Okay. Alright, so how to know galvanic protection is by looking at the electrochemical series, of course, or the the alloy, I think series. From there, you know that which metal that you should pair to become anode or become cathode. As I mentioned, normal cathodic protection is actually for a small area. Okay, a smaller area that this I think cathodic or maybe a sacrificial anode can cover. Okay. For a bigger structure, then we will use ICCP, impressed current cathodic protection. This is actually for a bigger area, a few kilometers away, or for example. So we need to put current, to press it with current, suppress it with current as a supply. Okay. ICCP system use anode connected to DC power source, and impressed current system employ inert anodes and use an external source of DC power, a rectifier, to impress a current from an external anode to the cathode surface. Anodes for ICCP are tubular and solid rods, shaped or continuous ribbon or various specialized material. So these include high silicon cast iron, graphite, mixed metal oxide, platinum, niobium, coated wire, and other things. Okay. So the same concept, okay, as cathodic protection, except that for this ICCP technique, you should draw or you should add the rectifier as the supply. Then it can actually, the current flow can occur. If let's say that it is a few kilometers away, a few distance away. Moving on to the next one, anodic protection. So anodic protection actually occurs in the severe environment, especially in a strong alkaline or acidic environment. Okay, in this case, metal to be protected will become anode. Okay, in practice, okay, the metal environment potential is held in the passive region by polarizing the structure in electropositive direction, where the passive layer is the most stable. Historically, anodic protection has the widest application process industry, and in particular on mild or stainless steel equipment used for concentrated sulfuric acid storage. Equipment such as pulp and paper mill digester and paper industry, they will use anodic protection because they use a reactor. And recausticizing that use white, green, and black liquor, clarify the storage tank, have been also effectively protected. Here, the metal potential is shifted to a passive zone from the active region by application of a direct current. So in this case, what happened is that the metal, to be protected, you oxidize it first. Okay, so the strategy is to oxidize it initially. Even though we say oxidation, maybe you relate it with corrosion, but actually the aim of this oxidation is to produce passive layer. If you have a passive layer, in the end, what happens is that it is stable. It becomes stable. Then no corrosion will occur. Right? So in this case, if you want to do anodic protection, it is best if you actually include chromium, chromium or whatsoever. Then the surface will be passivated with chromium oxide layer, and then finally you can actually do the process in high acidic or high alkaline without having a damage on the structure. A comparison between cathodic protection and anodic protection, you can see it from here easily for installation, cost and whatsoever. And finally, we have a proper design. So proper design actually, it is good practice if you want to make the material longer. I mean, use it for at a longer period. So in this case, you need to design a material that actually have a lower tendency for erosion or mechanical effects to occur. Okay, reduce the mechanical effect. Then it will actually reduce the corrosion process as well. So you can see from here, don't actually design a material that has a trap, water trap like this. If you have a design that didn't produce any water trap, then it can actually reduce the chances for corrosion. Right, so far we have looked into what will be the techniques for corrosion protection, okay? Either by material selection, controlling or modifying the environment, okay? Impress current, applying coatings, and finally a proper design. And the very last part in this topic is actually on the deterioration or degradation of material. So you know that different types of material will have different reactivity. For example, like ceramic. So ceramic is actually not, it is corrosion resistant because it's not made from metal. It is also chemically resistive. It cannot react with different types of chemical because it's mainly made of inorganic materials. But the main problem is that it is brittle. You learn this in mechanical properties that when you have a brittle material, it is hard, but after certain types of stress, then it can easily fracture. Okay. All right. At the same time, it cannot withstand too high physical, contact like high pressure or whatsoever. And then it can easily crack and damage. Even for polymer, okay, polymer can be degraded if it is etched with light, UV, for example. So that is why you see a lot of plastic become degraded after certain years or certain months of exposure under sun. Because the sun, you have UV, it can actually cause aging, and this radical will, cut or scission, bond scission due to the oxidation and finally becoming brittle and damaged. Okay. Polymers also can easily react with organic solvent, okay, because it can make the material become soft and others. Right? Degradation also will change the molecular weight of a polymer, and other factors will be related with mechanical factors. If you have a creep, dimensional instability, orientation relaxation, then this also can degrade the polymer. Okay, so for chemical effects of polymer, as I said, if the polymer has been introduced or you put chemicals inside, so what happens is that the linear polymer can be attacked due to a random scission, depolymerization, or it can be both. Right? And also you will have a sterilization effect due to a dry sterilization. This, of course, in the case of exposing it with temperature, sterile temperature, 160 to 190. So what happens is that for metal, you can do sterile. It can withstand that temperature. But for polymer, if you do sterile, then what happens is that it will be absorbed and it will actually destroy the structure of polymer. And finally, we have a composite. The environment of composite. Composite is mostly a combination between maybe polymer with other things. And composite is considered to be one of the best material because it can withstand chemical and it can withstand the mechanical effect as well. Okay. If the properties of the single component are degraded, then the whole composite will be affected as well. So this actually part of the weakness. So, Alhamdulillah, we finally finished with chapter 11. So we have learned about corrosion, of course, the definition, types of corrosion, how to calculate corrosion rate, corrosion protection methods, and also what actually cause the degradation of ceramics, polymers, and also composite. Okay, so actually that marks the end of our lesson for KIT 257. Alhamdulillah. And I think those who are celebrating Chinese New Year, you can celebrate it without having any class tomorrow or day after tomorrow. But of course, next week, Monday, next week, Monday, 10 a.m., we are going to have tests. So make sure that you revise your chapter, especially from my part, starting from phase diagram until chapter 11. And then after that, maybe look back into your quizzes, your assignments, and whatsoever. I think I would like to take this opportunity as well to request you to go for the online assessment, penilaian kuliah, available from the e-learning. I really hope that the 90 students inside KIT 257 will evaluate this course. You will evaluate me and Dr. Chua. Please give suggestion and please actually comment what do you think about the lecture, what do you think about the lesson, so that me and Dr. Chua can improvise from time to time. Okay, and inshallah, maybe before our exam will be on 17th of February, morning 9 to 12. Before that, before 17th, I will conduct a non-compulsory tutorial just to discuss or to get any question for you guys, and then we can discuss before your exams. Okay, and that's also the two things. I need your cooperation for the online assessment. Okay, and then we will have a tutorial. I will announce the date later. Okay, it's not compulsory. You can join or you don't have to join it as well. And finally, to submit your video presentation by end of this week. So what you need to do is to upload it in your drive and you share the link with me. Make sure that you make it accessible for me to download the videos or to evaluate. Okay, right. So I think I will stay for a while if you have any question. But if you don't have any question, then I will adjourn the class. Thank you very much for your kind attention for the past few months following this, I think, course with me. And I think I also would like to take this opportunity to wish you all the best for your exams or for your tests and whatsoever. Okay, so if there's any weakness from my side, I apologize. And everything is actually, every human have its own weakness. And I really hope that you enjoy your lecture with me. So with that, thank you very much. And Assalamualaikum warahmatullahi wabarakatuh. Goodbye all. Thank you very much.